y minus 2 equals x minus 4 squared. Restrict the domain. So the inverse is a function. And then graph the restricted function. That's number one. Number two, y equals negative 7, x plus 4 minus 3. I want the transformations asymptotes domain and range.
You want us to graph the inverse too?
Yeah, but the restricted one, the restricted original, and then obviously the inverse from that restricted original. It's not going to have two arms. Okay? Why don't you do 1 and 2? What's the first thing I have to do with the first one? Is the y by itself? Yeah. So what do we have to do? Add 2. So we're going to get y equals x minus 4 squared plus 2. Then I know that my normal parabola has been moved 4 to the right and 2 up. We agree? 4 to the right and 2 up. So you can type it into your calculator and get it that way. Or for me, I know I'm just moving my normal graph, which is 0, 0, is now going to be at, oopsies, 4, 2. And then this is going to be at 3, 3, 5, 3. Normally it's at 1, 1, 2, 4. So 6. But you can just pull them off your calculator if you're stuck on that, right? But that's your graph. We agree? And we connect it and we good. However, I want you to restrict the domain so that the inverse is a function. If I drew a horizontal line through this function, would it pass it? No. And if it doesn't pass the horizontal line test, the inverse won't pass the vertical, so the inverse isn't a function. So I want to get rid of one of the arms. I'm going to keep this one because I feel like it. You could have kept the other one. It's totally fine. Just that if you keep the other arm, you have to make sure you actually draw the graph that goes with it. So I'm going to restrict my domain to be x such that x is greater than or equal to 4, XER. You could use 5, 6, 7, 8, whatever you do. The key thing is that you have to draw the actual graph that goes with it. So the best way to do that, in order to draw an inverse graph of the one you already have, is take the coordinates they give you and then do what with them? Flip them and redraw it. Correct? So if we're at 4, 2, we're now going to be at 2, 4. If we're at 5, 3, we're now going to be at 3, 5. And then if we're at 6, oh goodness, 6, 6, it's now going to be at 6. Really? This is not drawn well to scale. 6, 6. So it's going to go like this. Now wait a second. There's an invariant point. Why is there an invariant point? The x and the y's are the same, correct? How can we look for invariant points? We draw the line y equals x, and however many times it crosses through on the line y equals x, we're going to get invariance, because when y equals x, x equals y. The points will be the same. So if I have like 1.2, 1.2, it's going to be 1.2, 1.2. Okay? You could have done less than, but then you'd have this arm up here, and then you'd have another arm going that way, I think. They just scoop out the two arms. Okay. This one, we need transformations. So we have a vertical stretch By a factor of what? Of 7 about the x-axis. We have a reflection in the x-axis. We have a horizontal translation. 4 units left. And a vertical translation. 3 units down. I didn't ask for mapping, but if we did do mapping, our x would only have what happening to it? X minus 4. And then our y would be multiplied by negative 7 and then subtract. I didn't ask for mapping, I'm just saying if we did do it. Now, the asymptotes. An x equals asymptote is a what asymptote?
Horizontal translator.
Horizontal translation will get you the what asymptote?
Horizontal.
Nope. Vertical. X equals gets me vertical asymptotes, and y equals actually gets me horizontal, because y equals 3. If I went to go draw it with my finger, I'd go to 1, 2, y equals 3 if I put a slash through it. And what way would I be going? Horizontally, correct? And if I went like x equals negative 4, which is what this one's going to be, I'd go 1, 2, 3, negative 4, and then I'd put a slash, and where would my slash be? It's an up and down slash, right? When I cut through the x-axis, I'm vertical. So all horizontal lines are y equals lines. All vertical lines are x equals lines. So I know that x can't equal negative 4. I know that. And the reason why it can't equal negative 4 is because if it did equal negative 4, my denominator would be 0, which is wrong and illegal in every territory, state, province, everywhere. So I know that I have an asymptote. An asymptote is where it does not exist, right? And it's an x equals, so I know I have a vertical asymptote. At x equals negative 4. Because the asymptote's where the asymptote actually exists, so it's equal to. But it's a dashed line that doesn't exist. It's where the graph doesn't exist, but it's where the asymptote does. Now, if it's in transformed form, which this is transformed form, a over bx plus c plus d, right at the back, this is transformed form. If it's in transformed form, your vertical asymptote comes from here, but your horizontal asymptote, I should keep that negative in there, comes from there. So I have a horizontal asymptote at y equals negative 3. If you can get those really easily, your domain and range is really easy, because your domain just can't equal that, and your range just can't equal that, right? So if you can get your asymptotes, your domain and range is easy. So, I'll have my domain and range down here. My domain is going to be just not equal to 4. So x, such that x cannot equal negative 4 xer. If I wanted to do it in interval notation, remember we would go from negative infinity to negative 4 round bracket, or negative 4 to infinity. That's an interval notation. My range is y such that y can't equal negative 3 yer. So it would be negative infinity to negative 3, or negative 3 to infinity. Okay? Yeah.
What causes you to get on course? Because like your vertical one is just because you have a denominator of 0.
It's because the denominator of 0 causes your horizontal one to happen. So wherever that one exists, the y can't exist, kind of thing. Yeah. And we're going to get points of discontinuity as well. So yeah, it's that crossing section where that point doesn't exist, which causes all the x's and all the y's not to exist. Okay, so we're doing the last lesson of rationals today. So this is rationals part 2. So we did rationals. The first one was in transformed form, right? We had a over bx minus c plus d. And we could just pull our asymptotes right from the equation, correct? Now we're going to do ones that aren't in transformed form and ones that are actually quadratics as well. So this is rationals part 2, and you're just writing it out. It's easier to do than typed, and not one photocopier is working right now. Very well. Rationals part 2. So we're going to go over what happens when you have a numerator is a smaller degree than a denominator, your numerator is the same degree as your denominator, or your numerator is a larger degree than your denominator, what happens? Okay, so that's the first way we're going to look at this. So the reason why this is different than yesterday is part 1 was in the form y equals a, b, x minus c plus d. This is transformed form. We're just going to write this as a little reminder. And in transformed form, you can state all the transformations. That's what it's good for. Also, the other thing it's good for, I don't know why that just bumped, is your horizontal translation is your vertical asymptote. And in this case, x equals c. Here are your vertical translation. Is your horizontal asymptote. Y equals d. So that's what we went over yesterday. So this is transformed form when you have that plus d sitting at the back, right? What we're going to go over is what do you do with rationals when they're not in transformed form, when it's like something all over something. There's no plus d at the back. Okay, what do we do? So we're going to look at the different cases. So this would be case 1. Numerator degree less than denominator degree. Numerator degree is less than denominator degree, and I'll show you an example. So we have y equals 7 over x plus 4. So the degree is the largest exponent number, right? So when we have y equals 7 over x plus 4, our degree of the numerator is actually x to the 0. So it's degree 0. And then this one is degree 1. So the numerator is a smaller degree than the denominator. We agree? When that happens, we still do our vertical asymptotes the same. That doesn't change. Our vertical asymptotes come from our non-permissible values. Okay? So our vertical asymptotes are what our non-permissible values can't be. So if I have x plus 4, what can't x plus 4 equal? What can't this whole thing equal? 0. So if I go to solve it, I'm going to subtract 4. X can't equal negative 4. And then we can check to see if we're right. If I plug negative 4 back in here, I get negative 4 plus 4 is 0. So I know I'm right. So the vertical asymptote is easy to find every single time. It's just the non-permissible value. It's what x can't be. And if it was, My denominator would be 0. The y's are the harder ones. So I have my vertical asymptote immediately. And remember, asymptotes are where they exist. So the vertical asymptote is x equals -4. Nothing different than what we did yesterday. My horizontal asymptote, I could actually put this into transformed form, couldn't I? This one in particular. I have a number, so that's a over bx plus c plus d. What would my d be, though? 0. I'd have a plus 0 as back, wouldn't I? Something to memorize is if your numerator is a smaller degree than your denominator, so when this happens, your horizontal asymptote is always y equals 0. Every single time. So if your numerator is a smaller degree than your denominator, it's always y equals 0. Okay? Then we're going to do case 2. I don't know why it keeps moving on me. Case 2, what do you think we're going to have? The numerator degree, other one. Can't, if you don't have a larger and you don't have a smaller, you have equal. Numerator degree equals the denominator degree. So an example could be like y equals 3 minus x over 4x plus 1. What's the largest exponent in the numerator? 1. What's the largest exponent in the denominator? 1. I think I'm about done with this thing. Moving on. So both of these are degree 1. Even though they're out of order, right? They're degree 1. Does everyone agree with that statement? Where does my vertical asymptote come from? It doesn't matter if it's degree 1, the same degree, large degree, smaller degree, equal to degree. Where does my vertical asymptote come from? Yeah, it's from the 4x plus 1. It comes from your non-permissible values, right? Your vertical asymptote is what x can't equal. So I just always go to my denominator and I say 4x plus 1 can't equal what? 0. Subtract my 1. We did this last year in 20-1. 4x cannot equal -1. Divide by 4. X cannot equal -1/4. So that's what it can't equal. So what's my vertical asymptote at? X equals -1/4. Because the asymptote is where it exists, where that dashed line exists. So I would go to a -1/4, a little bit beside the y-axis, and I'd make a vertically dashed line at x equals -1/4. Okay? Now, when the numerator was a smaller degree than the denominator, my horizontal asymptote was y equals 0 every single time. When the numerator is the same degree as the denominator, when this happens, your horizontal asymptote is a fraction of the leading coefficients. So what are the leading coefficients? The leading coefficients are the numbers in front of the largest degree. right? The numbers in front of the largest degree. So my largest degree here is x to the 1, correct? So the leading coefficient of the numerator is -1, and the leading coefficient of the denominator is 4. So it's going to be y equals -1/4. Did those have to be the same number? No, I just randomly made them the same number by accident. Kind of worked out. But they don't. Okay? So case 1, numerator is smaller degree than denominator. Case 2, numerator is the same degree as denominator, so your horizontal asymptote is a fraction of the leading coefficients. Has my vertical asymptote, the way I found that, changed? Nope. Okay? Case 3. What do we have left? Numerator degree. Yeah. So we have y equals x squared minus 4x minus 3 over x minus 3. Yeah.
For the first one, about the horizontal asymptote, is it always the reciprocal of the leading coefficients? Like if it's positive, it's negative.
Which one?
Like for the first one, 1/4. Like is it always like reciprocal of the positive and negative? Because it was 4x.
Not really. Because if it was like 3x plus 2, then it would be -2/3. You have to just solve for x. You're just finding the non-miscible value of what would make your
Yeah, it would be the
denominator.
vertical, but for the horizontal.
It's just a fraction of the leading coefficients.
So why isn't it just 1/4? You said it's just.
Because it has a -1 sign in front of the number. It's a -1. The leading coefficient is a -1. So you take -1 over 4. You just take whatever signs in front of the number with it.
Oh, on the numerator part though. Right?
Yeah. The numerator is -1, yeah. So if the number in front of the x to the 1 is negative, you take it. If the number in front is positive, you take it.
Yeah, it's the numerator that determines if it's.
Nope. You just take this.
the.
You just take the sign with, so guys, quiet. Guys, quiet. So if this is x to the 1, -1 would be the leading coefficient. This is x to the 1, 4 would be the leading coefficient.
Yeah.
But if this happened to be a -4, I would take -4 with it.
Yeah.
It's just whatever the numbers are. So if it's a negative divided by a negative, it's going to turn positive.
Yeah.
If it's a positive divided by a negative, it'll stay negative. So you just take the numbers that are in front, and then whatever signs are there is what it makes it. It's not always going to be negative, always going to be positive. It depends on what the
signs
coefficients
at
are.
the front, so it's just 4 then.
We're taking a fraction of these two red numbers and making a fraction.
Oh, two red numbers, okay.
Yeah. Because it has to be the ones that are in front of the x to the 1, Sean. Do you see this? It has nothing to do with the 3 or the 1 at all. Yeah. Okay. Numerator degree is greater than the denominator degree. The moment you have a quadratic, what do you have to do? Quadratic is a degree 2. Quadratic is the numerator. What do you have to do? Factor. You're going to have to factor that top every single time. So whenever you have a rational expression with a degree 2, on the top or the bottom, you have to factor. If you can't factor, I'm not joking, you have to start admitting it. Come in and get help. Or the year's going to suck. So we go, what times what equals, this should be a +3. It's never going to work, so that's -3. What plus what equals +3? And then what times what equals +3? What plus what equals -4?
-1 and -3.
-1 and -3. If I had left it the other way that I said first, there's no way it would work. Now I can go straight up to brackets only because there's a 1 in front. So I get x minus 1, x minus 3. And remember, if you can't do product sum or decomp, or that doesn't make any sense to you, or you don't have a method that you were taught, like the cocoa shop or whatever that works, Come in and get help. So, x minus 1, x minus 3 goes on the top. And then on the bottom I have an x minus 3. Now, I told you that the vertical asymptote comes from the denominator. We agree every single time? Except if they cancel. Now I'll show you why. So when we did the other ones, we got asymptotes, vertical asymptotes and horizontal asymptotes, dashed lines. We agree? But this denominator is going to completely go away, isn't it? Because I have matching things. So when I have matching things, these ones that cancel off, if I can physically cross them off, it's not a vertical asymptote. It's actually, and you can cancel factors, it's called a point of discontinuity. So now you don't have dashed lines, you have a graph that's drawn perfectly with an open dot. That's what that means. And we'll show it to you in a second. So you have a point that's open. So this is something to note as well. If you have a vertical asymptote, you will have a horizontal. They go hand in hand. Okay? If you do not have a vertical, you do not have a horizontal. So do I have any vertical? Do I have any factors left over after I cross that off in the bottom? Nope. So all I have is a point of discontinuity. I do not have any asymptotes. Okay? Now a point of discontinuity is a point, a coordinate, which is an x and a y. We agree? Where does the x happen at? If we have x minus 3, where's the x of my point of discontinuity at? It's at 3, because 3 minus 3 would get me 0. So I have the x. And I find it the exact same way I would find my asymptote. I would go x minus 3 can't equal 0, x can't equal 3. So I have the x of the point of discontinuity. So that 3 doesn't exist on the graph. There's an open dot at it, right? 3 and something. I just don't know what that something is, that y. How do I get the y? Does anyone have any ideas how you could get the y? Plug it into the x minus 1. Plug it into the simplified one. If I plug it into here, I'm going to have problems because it'd be 0 and 0, correct? But if I plug it into the leftover equation now, and I'm going to do it here so we can see it, we're going to have y equals x minus 1. And now we have y equals 3 minus 1. So y actually equals 2. Now whatever this simplifies to, y equals x minus 1, this is what the graph actually looks like. So what kind of graph is this? It's linear, it's a line. It's still a rational graph though, because a linear graph is a straight line that never ends. X-ER, Y-ER, boom, keeps going, correct? This is a rational graph because it's actually a line at x minus 1, but there is an open dot at 3, 2. So if I go to sketch this so that you can see what it looks like, you can type in your calculator after. If I go to sketch this, awesome, I'm so glad I did that. Okay, if I go to sketch this, I have a graph at x minus 1. So before I even go to draw it, I'm going to put my point of discontinuity. So at 3, 2, I better have an open dot. So if my graph draws completely above or below and doesn't get with that dot, something is wrong. You either drew your graph wrong or your point of discontinuity is wrong. Because I just need to have an open dot at 3, 2. So now I'm going to sketch the line and hope to goodness it passes through there. Okay? How do I sketch a line? This is grade 10. It's a little rocky for some of you. So this is my y-intercept, right? So that's my starting point. That's like, here's where we stand to start drawing. That's what this is. The y-intercept, in grade 10 you're taught, that's like the starting point. It's where they have like the paper where you would stand and you'd be ready for your race, right? So at minus 1 is my starting point on the y-axis. And then my slope tells me, it's like a little map that tells me how I keep going to keep walking, right? Like that's what that slope does. So in grade 10 when I used to teach it, I used to have kids who would go -1 and then they started 0, 0 and do their slope. That's not how it works. Yeah? Yeah, tell me. So my slope is actually 1 over 1. We agree? And what do? Do you rise before you run when you get out of bed, or do you run before you rise? If you're in bed. You rise before you run. If you're running before you rise, you're just running in bed and you look stupid. Okay? So slope is like getting out of bed. You need to rise, and then you need to run, because you're probably late. So I'm going to rise up 1 and run right 1. So this is my starting point. This is where the little line is that says, Lepp, start here, right? It's like a treasure map, really, but it's a straight line treasure map, so it's kind of easy. And then we need to go up 1, right 1, up 1, right 1, up 1, right 1, and you're like, please let it cross through the stupid point of discontinuity so I'm not wrong. Up 1, right, but I can't fill it in, correct? Because it doesn't actually exist there. Then I go up 1, right 1, up 1, right 1, and then how do I go the opposite direction? Completely opposite. Down 1, left 1, down 1, left 1, and we'll pretend this is straight, but it's not. It's supposed to be perfectly straight. It's super not. It's a perfectly straight line. Imagine it. I believe in you. You can pretend that it's perfect. Perfect everywhere. Okay, so if you type y equals x minus 1 in your calculator, is it going to draw the point of discontinuity? No, because you're just typing in the linear. So what do you actually have to type in if you want to see the point of discontinuity? The actual original equation. So type this into y1 and y2. Or not y1, y2. Into your y equals as a fraction. So you can either, if you're going to type it in, how does it know it's a fraction? It can go like this. Oh, I already have brackets. So we can bracket the numerator and bracket the denominator, and if you have the older calculators, that's the only way you can type it in. If you have the new ones, what could you do? You go to y equals, and you go, alpha, y equals, and then enter. It'll pop up a fraction for you. Remember? I taught it this year, twice. Y equals, enter. Ooh, that's from yesterday. So we go alpha, y equals, enter. Now we have to type in x squared minus 4x plus 3 over x minus 3. And then you don't need brackets if you use this one. Now when I press graph, you might miss that there's a point of discontinuity, correct? Most calculators will not draw it, because most of your calculators are actually, especially the old ones, are made to believe that all functions are continuous. So in the older calculators, when it draws a rational, it'll like draw the rational, and then it'll keep connecting the asymptote to it, and then it'll continue to draw the rational, because it's like all graphs must be continuous, but they're not. So how can you check? Well, we can go like this. We can go second, trace, value, and what's my point at? What x? 3. There is no y. So it's an open dot. Yeah. The other way you can do it, and this is the way that works for everything, because if there's fractions and stuff, you can type it in. Like if x was a half, you could go second trace value a half, and y will come out as error, or nothing there, right? But if they're whole numbers, you could just go second graph, and you'll see at 3 there's actually an error. The only problem is that if your x is like half, it's not on the table, right? Yeah.
What's the difference between going second trace value and then instead of just pressing trace and then typing?
So if you press trace often will just trace. It's not actually going to get you close to it. And some of the calculators will let you type in the x value and some of them will not.
This is like when I press trace, I can just put in anything and then it'll tell me what the y.
Not all of them will do that.
Oh.
So I kind of got away from that. Because what people will do is instead of typing the value in, they'll use their arrow and they'll try and get as close as they can to 2. And they're like, it's 3.1. And I'm like, no, it's 2.7. Like, these are not the same thing. So it's just more accurate the other way. Yours works that way. They don't all. The new ones stopped doing that. Okay. So we've went over degree of numerator less than degree of denominator. My horizontal asymptote is always y equals 0. The degree of my numerator is the same as the degree of my denominator. I take the leading coefficients. That's my horizontal asymptote. Then I did this one where the whole denominator completely canceled off. I get a point of discontinuity, correct? even if the whole denominator doesn't cancel off, I get a point of discontinuity. So I'm going to give you 3 questions, and you're going to give me the horizontal and vertical asymptotes or points of discontinuity for all of them, and then we're moving on to one other type. If they're the same degree, but degree 2, degree 2. Yeah.
Dip.
Can you what?
Undip.
No.
Why?
Because we're not, it's once a month. It's
Yeah,
not.
This is the
This
one.
is my time.
No. Yes, that was a good question. Not a good question. Yeah. I was like, yeah, I'm like, where are you pointing? Okay, so here's your examples. Example 1 with a really large marker. It's going to be y equals negative 3 over x 2x plus 1. That's a scary situation. 2, y equals 2 minus 3x over 4x plus 3. And then 3, y equals x squared minus 2x minus 3 over x plus 1. So I want the vertical and horizontal asymptotes or points of discontinuity, whatever is there. Okay? Do that. So, the numerator is smaller than the denominator. So let's do the horizontal asymptotes first. Okay? Because they use the rule, right? The rule of numerator greater than denominator, numerator less than, numerator equal to is all based for the horizontal asymptote. The vertical asymptotes are all found the same. Denominator, 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 right? So the horizontal asymptote, if the numerator is a smaller degree, this is x to the 0, this is x to the 1. Horizontal asymptote is at what? Y equals 0 every single time. You're like, what about if it's not? It is every single time. If the numerator is a smaller degree than the denominator, it's y equals 0. My vertical asymptote is based off of my non-permissible value, unless it cancels off, like it did in the last example, right? But 2x plus 1 is not canceling off. We agree? So how do we find our horizontal asymptote? We take that denominator, 2x plus 1, and we say it can't equal 0. Subtract 1. 2x cannot equal negative 1. Divide by 2. X cannot equal negative a half. So my horizontal asymptote is actually at x equals negative a half. Now what would I do with my domain and my range? It would be just like yesterday. Domain, x such that x can equal negative a half, xer. Y such that y can equal 0, yer. Right? Nothing crazy. If you can get the asymptotes and the points of discontinuity, your domain and range are really easy. They're just not equal to them. Okay, number 2. The degree of my numerator is degree 1. The degree of my denominator is degree 1. So my horizontal asymptote, when they're both the same degree, is going to be a fraction of their leading coefficients. The leading coefficients are the numbers in front of the x1s, correct? So this one is negative 3, this one is 4, so it's negative 3 over 4. My vertical asymptote, once again, because the denominator didn't cancel off, it's not a point of discontinuity, my vertical asymptote is just my non-permissible value, what my bottom can't equal. So 4x plus 3 cannot equal 0. I did it again, unintentionally. I made them match. That was my brain just keeps wanting to make them the same. They're never, like, it's rare. Like 0.5% of the time are these two the same. I just happened to somehow did it twice. I did not mean to do that. Don't be like, oh, they must all be the same. They're not. My brain did it again, and not intentional. Okay, anyways, negative 3. 4x cannot equal negative 3 over 4. So x equals negative 3 over 4. Again, how did I do that twice? I don't even know. Okay, we factored the top. What multiplies to give me 3 and adds to give me negative 2? It's going to be x minus 3, x plus 1. And the bottom is x plus 1. So the bottom is going to cancel off. So it's no longer a vertical asymptote. It's a point of discontinuity. And points of discontinuity are points. So that means you need a y. The moment that the diploma asks you or I ask you to find the y value, I'm giving you a standard of excellence question. So if I only ask for the x value of the point of discontinuity, that's just a plain old normal question. And if I ask you for the y, so this is like the nicest standard of excellence in my head. Like you literally just plug the x back into the simplified one. The standard of excellence, 25% of your diploma, and your unit test should be, it's the harder style. Not always harder, because that I don't feel like is a harder thing. So we know x is equal to what? -1. And then to find our y, we plug it back into the simplified one. So it's going to be -4. Now, once again, does the -1 and the -4 both don't exist, right? They're an open dot. So if I did domain and range on here, domain would be x such that x can't equal -1, xer. My range would be y such that y can't equal -4, yer, right? Now, there's one more type. Same degree, but not degree 1. So there's like a degree 2. Top and bottom, and one of them cancels off. Okay? So, let's go here. Last example. This is the special example. It comes up a lot, and it's not hard. It's not hard. It just kind of uses a point of discontinuity in a numerator and denominator same degree. Okay? So, we're going to go y equals x squared minus 2x minus 3 over x squared minus 4x minus 5. So degree of the numerator is the same as degree of the denominator. We agree? However, they're degree 2 functions. So the first thing you have to do is factor. We do nothing with them until they're factored. Okay? So if your numerator or your denominator are both are quadratic, you need to factor them. So I'm going to get x minus 3 and x plus 1 in the numerator, and then x minus 5 and x plus 1 in the denominator. Wait a second. These cancel. The moment two factors cancel, what do you have?
Anarchy.
Not anarchy. You have a point of discontinuity. So from when these cancel, we're going to get a point of discontinuity. And it is at -1 and something. How do I get the something? I'm just going to plug it back into a rational instead of a line like last time. I'm going to plug it back into here, the simplified version. So I'm going to go y equals -1 minus 3 over -1 minus 5, which is -4 over -6, which is 2 over 3. So I have a point of discontinuity, and last time that was it, we were done, correct? But last time my simplified equation was just a line. So I had a line with an open dot. We agreed? This time my simplified equation is actually a rational. Did the x minus 5 cancel? No, so it's not a point of discontinuity, it's a what? A vertical asymptote. So can I have a point of discontinuity and a vertical asymptote? Yes. If you have two factors in the denominator, one cancels off, it's a point of discontinuity, the other one doesn't, it's a vertical asymptote. So here I have a vertical asymptote at x equals what? 5, because 5 minus 5 is 0. And my remaining rational is degree 1, degree 1. So how am I going to get my horizontal? A fraction of the leading coefficients. This one's a 1 and this one's a 1. So what is it? 1. And to be honest, this one's done the worst for domain and range, because people will either put the horizontal and vertical that they can't equal, or the point of discontinuity that it can't equal, but they won't remember to do both. Y equals 1. So if I went to do domain and range here, my domain, I have two values that don't exist. I have an open dot and I have this one, right? Open dot and I have that one. So my domain is going to be x such that x can't equal 5 because of the asymptote, and -1 because of the point of discontinuity, xer. And my range is going to equal y such that y can't equal 1 because of the asymptote, and 2/3 because of the point of discontinuity. Y-E-R. Now go type the original back into your calculator. So type in x squared minus 2x minus 3 in brackets if you're not using the fraction button. And then divide by that. Type that in. So what am I expecting? I'm expecting a rational graph with an open dot, right? I have an asymptote, and an open dot. That's what I'm expecting. So if I go alpha y equals enter, or bracket the top, bracket the bottom, x squared minus 3, is it 3x minus 4? I can't remember anymore. 2x minus 3. Thank you. And then x squared minus 4x minus 5. So look, I have a vertical asymptote at, what's this at? I typed something in wrong. Oh, I have a vertical asymptote at 5. I have a horizontal asymptote at y equals 1. I can't just draw them. And then I should have an open dot at 1 2/3. Does it look like I have one there? No, because my calculator won't show it. So how many of you will forget to draw it when I make you graph a rational on the test? A lot. So we're going to stop that, and we're going to still draw it, right? Because you see the asymptotes, you'll draw them, but you forget to do the open dot, right? So if I go second trace value 1, was it 1? What was it? -1. I just drew that in the wrong spot. Nope. You're just gonna deal with me. That's 1 and 2. Whatever. Second trace value -1. Oh, there's an error there. Good. Great. Awesome. I was doing so solidly, and then just the end. Now I have like a vortex on there. It's fine. Okay. Page 451. We have one little thing to still go over. If I give you a graph of one of these, how the heck do you come up with the equation? But we're doing that tomorrow, not today. So page 451. Number 1. And then 4 to 6. 5 and 6 are matching. So you're going to have to the hardest part of 5 and 6 is factoring. Oh, what about this? So if I give you this, x squared plus 2x over x squared plus 4. Can I actually factor an addition of squares? No, that baby's staying the same. Can I do anything to this? Yeah, I can take a GCF. Everyone forgets the GCF ones. Everyone forgets the GCF ones. Just do 6. 5's stupid. Look, there's a comma. It just became. 5 has like it's not stupid. One of the 4 is stupid, and then it confuses everyone, which is, it's that example. So, meh. 1, 4, 6.